Hi everyone, welcome back. This is another lecture on design and application of lasers. I'm your instructor, Dr. TJ Hammond. Again, we'll be covering absorption, emission, and dispersion, which is chapter 3 from laser physics textbook. So why are we covering absorption, emission, and dispersion? So we're finishing up with this concept, this lecture. Basically, it's that we want to understand how light interacts with matter. So last week we looked at these discrete energy levels that atoms and molecules can have, and solids can have these bands. We want to understand when light comes in, what happens if it's of the energy that could excite one of these transitions, so it's equal to one of these discrete energy levels, or what happens if it's in between these levels, what happens if it doesn't get absorbed. So your daily assignment for Monday is, I could tell that a lot of people weren't really following along with what I've been discussing on Monday and especially Wednesday's lecture. And so I want you to think back about what we've learned this week and kind of list some points that you do understand, and also list some points that you don't understand that we could further clarify. So do that for Monday, and then we can if there are any points that people are still wondering about, maybe we can discuss those points next week. Okay, so I'm going to try and clarify some of this explanation for what's going on when light interacts with matter. So what we have is an electromagnetic wave. So we have this light. Light is an electromagnetic wave. That's what's been proven from Maxwell's equations. And it comes in and it oscillates with a frequency omega, and it has a period, a spatial period lambda, that's given as 2 pi over lambda is equal to k. So this light wave is oscillating in x, it's polarized in x, and it's propagating in z, and then that hits this atom here, which is composed of an electron, and we're going to model this electron as attached by a spring to some nucleus. So what we're going to say is, since it's an electron and it's attached to a nucleus by a spring, then by Newton 2, the second law of Newton's second law, that there'll be a force on this electron caused by this spring. We're going to say there's some unknown generalized damping term, and there's going to be some electromagnetic force on this. So if you remember, we have the Lorentz force. We're going to ignore the magnetic field for now, and we're going to say that this force is equal to the charge of the electron times this electric field. So where this field is, of course, oscillating. Now, the force of a spring is, of course, negative kx. So negative k is this, or k is the spring constant, and x is the displacement from equilibrium. And then we have some damping, which we're going to say is m, the mass of the electron, times gamma, which is this damping factor, times x dot. And so what that means is that this damping force is proportional to the velocity. So if this thing's going fast, it's going to have a larger damping than if this thing's going slowly. And so this is because we can understand the solution well. We know this from driven damped oscillations from like a spring or a pendulum or something like that. And it seems like it works quite well with these systems, with an electron in an atom. So we then solve for this one electron motion, and so what we get is the acceleration of this electron is negative k over m x, where k over m is, of course, the resonant frequency squared, or omega naught squared, minus gamma x dot, so that's again this damping term, and then minus e over m e naught, and then that's multiplied by cos omega t, where cos omega t is this oscillating function in frequency. Now, what we've done is, if you notice, we've dropped the z dependence, and that's the dipole approximation. So basically we're saying that this wave interacting with this atom, this atom doesn't really see the wavelength of this light. It sees this light oscillating up and down in time, but it doesn't really see any spatial dependence on this wave. And that's a dipole approximation, and we're kind of justified in having that dipole approximation because a wavelength of visible light is on the order of 500 nanometers, or a lot of lasers where it could say like 1 micron, so 10 to the minus 6 meters, whereas the size of an atom is on the order of half an angstrom or an angstrom, so that's 10 to the minus 10. So this guy is 4 orders of magnitude smaller than this guy, and so we're going to say, okay, well, then this thing is so small that it's just not going to see any of that spatial effect. And that's where we get this equation from. Okay, now instead of using the cosine function, cos omega t, we're going to say we're just going to look at this in terms of a complex wave, and we're going to say this is e to the minus I omega t. So we're going to say that what happens is this electron is sitting in equilibrium. It sees this wave that pushes this electron up and down, and this thing can get pushed up to some maximum amplitude x naught and down to some minus maximum amplitude, so minus x naught. And this electron oscillates up and down, bobbing with this wave. So this is a second order inhomogeneous differential equation, and it has this general solution here that is complex, and that complex part comes from this damping parameter here. So what we're saying is that x naught, the amplitude of this motion here, is proportional to the electric field, so how strong we drive it, that makes sense. The charge of the electron, and that's basically telling us how this electron couples to this electric field, so that also makes sense. It's inversely proportional to the mass. That also makes sense because if this thing's really light, it's going to be really easy to drive this thing around. And then the denominator is complex, and it's omega naught squared minus omega, so omega naught squared is this resonant frequency, or it's k over m. And it's basically saying how close we are of this oscillating field omega to this resonant frequency omega naught, and so we're taking the difference of that. And then we have this complex part here, and that's dependent on this damping parameter here. Okay, so this is complex, but we can break it up into its real and imaginary parts if we multiply everything by the complex conjugate of the denominator, and that gives us a real part here where we get that the numerator is the difference between the square of the resonant frequency and the driving frequency, and the imaginary part, which is proportional to this damping parameter. Okay, so I realized that maybe there were too many concepts on Wednesday's lecture, so maybe I'll go back to some of the more basics of what's going on here. What we have is an electromagnetic wave. So this wave, as I said, it's polarized in, say, the x direction. It's propagating in the z direction. Now, in general, the wave equation is that it's a second order partial differential equation. Okay, it's a second order differential in space, so that's in the direction of propagation, minus 1 over the velocity squared, and oh, this is a typo. A second order derivative of this function with respect to time squared is equal to 0. So this is a wave that travels with a velocity v in the x direction. Okay, this has a solution of a, which is some amplitude, which is not determined by this wave equation, e to the I kz minus omega t. Now, for those of you who know complex numbers, you'll recognize that you can also have e to the minus I kz minus omega t, but of course that's just the complex conjugate of that. And so this is a second order differential equation, so it needs to have two orthogonal solutions, and so you could say this is a e to the I kz minus omega t plus a e to the minus I kz minus omega t, and then you'll recognize that that's cosine kz minus omega t, which is what we had said before. But we're just going to keep this complex notation here because it ends up simplifying the math. Even though it's complex, it ends up actually keeping the math simpler, ironically. So we'll prove that this is the solution by substituting it in. So if you take the second derivative of e to the I kz minus omega t with respect to space, then we get a negative k squared out front times this original function. And if we take the second derivative of this function with respect to time, we get an omega minus omega squared, but we have a minus already, so we get plus omega squared, and then we have 1 over v squared f. But in general, f is not 0, and so that means that if f isn't 0, then that means that for this equation to be 0, for this equation to be satisfied, then we have to have that k squared is equal to omega squared over v squared, or k is equal to plus minus omega over v. Now, if you remember what I said before, we can have a e to the I kz minus omega t and a e to the minus I kz minus omega t. Well, that's how you can get plus and minus here. Okay, so where if you have k equals plus omega t or omega over v, then what you get is a wave that propagates to the right, and minus omega over v gives you a wave that propagates to the left. Okay, so that is how we get the solution to the wave equation for a homogeneous wave equation. Okay. Now, what we actually have is, instead of just having a single electron attached to a single nucleus, we actually have a whole bunch of electrons attached to a whole bunch of nuclei. And so this is our ensemble of springy electrons that are sitting around in this matter. And so now we want to understand how light interacts with this entire ensemble, and we call this ensemble matter, because that's actually what we want to know, is what happens when this hits like air or glass or a semiconductor or something like that. So from Maxwell's equations, if we actually did the full derivation from Maxwell's equations to get the electromagnetic wave equation, you actually get this thing here. So what you get is, again, a second order differential equation, partial differential equation, in space and in time, but then you end up with an inhomogeneous part, this derivative of the current with respect to time. But if current is 0, so if these electrons aren't flying around, if they're kind of stuck to this nucleus somewhat, then we still get this homogeneous wave equation where you get, or say if this is, I guess if current is 0, if this is propagating through and nothing's happening here, then this is just going to be 0, and we get the homogeneous wave equation. So we have the second order derivative of the electric field with respect to space minus this second order derivative of the electric field with respect to time times this mu naught epsilon naught, so mu naught being the permeability of free space, times epsilon naught, which is the permittivity of free space, is equal to 0. But this looks exactly like our wave equation from before, where we had this, but we had in front was 1 over v squared. And so now we get this wave equation, but instead of this being 1 over v squared, we get mu naught epsilon naught. And so what that means is that this is how fast this wave travels. And so 1 over v squared is equal to mu naught epsilon naught, but these are fundamental constants, and so this is equal to 1 over c squared. So the speed of light is a fundamental constant because mu naught and epsilon naught are also fundamental constants. Okay, so this tells us that an electromagnetic wave in free space is going to be traveling with a speed of c. But what happens in general if we actually hit something that can move these electrons around? And so in general, the current is this charge density times the velocity, or x dot, but the polarizability of some material is given by this charge density and how much it separates from, what's the separation of this charge, of the positive charges from the negative charges, and that's called the polarizability. And so we can see just from how these equations relate to one another that the current is the rate of change of the polarization. But we said that the general form of this wave equation is that the inhomogeneous part is mu naught times the first order derivative of j with respect to time. But we just said that that j is equal to the derivative of the polarizability with respect to time. And so that gives us that this is actually the second order derivative of the polarization with respect to time. Okay, so in the linear case, we said that the polarizability is going to be proportional to the electric field. So we have this polarizability P is equal to epsilon naught chi E. And so that's assuming that this is linearly proportional to the electric field. Where we don't know what chi is, but we still know epsilon naught. So now we substitute that in to our second order differential equation here, and that means that we get our second order partial differential equation on the left-hand side, which is actually our wave equation, is equal to mu naught epsilon naught chi, and then the second order derivative of the electric field with respect to time. And so this is an inhomogeneous wave equation. But what this is saying is that the inhomogeneous term, the right-hand side, actually looks like the left-hand side. So what this is saying is we're coming in with an electromagnetic wave that's hitting this matter and causing this current, okay? Or causing this time-dependent polarizability. But this time-dependent polarizability, due to the linearity of this response of all these electrons oscillating around, ends up looking just like the form of this wave equation. And so now what we can say is we can lump this right-hand side into this second term on the left-hand side, and we get that the second order derivative of the electric field with respect to space minus mu naught epsilon naught, and then we now have this new constant, 1 plus chi, times the second order derivative of the electric field with respect to time is equal to 0. But this again is a homogeneous wave equation. But we've changed the velocity of this wave. Instead of it being mu naught epsilon naught, which is 1 over c squared, we get mu naught epsilon naught times 1 plus chi. And so mu naught epsilon naught 1 plus chi, we're going to call this, instead of being 1 over c squared, we're going to call this n squared over c squared. So n squared over c squared is equal to 1 over v squared. Or the velocity in our medium is c divided by n. And you're probably familiar with that because you've seen that before with Snell's law. So now our field has the solution. It's a homogeneous wave equation. So we get the second order derivative of the electric field with respect to space minus n squared over c squared, so this new velocity in this matter that has an index of refraction n, times the second order derivative of the electric field with respect to time is equal to 0. And so this now has a solution, again, just like what we had before for an electric field in free space, of E of z of t is equal to E naught, some amplitude that's to be determined, or dictated, e to the I kz minus omega t. Now, our differential equation is going to be, again, just like before, negative k squared E plus omega squared n squared over c squared is equal to E. And so what that tells us is that k, this wave vector, is equal to plus or minus omega n over c. Okay, so this is just like what we had before for our wave, but now we have that the velocity is dependent on this index of refraction n, and so we get that the wave vector is equal to omega over c times n. Okay, so that's what happens if we only were looking at this real part of the polarizability here. So we've only been assuming here that this is real, and so we only have everything here is real, okay? And so that means that our index of refraction is real. But x isn't purely real. This displacement of this electron isn't purely real. It's complex. We have the real part here, and we have this imaginary part here. So what that means is that our k isn't just a real part, but it's a real part plus an imaginary part, so I times ki, this complex part. So we stuff that into our solution for our wave equation, and we get that we still get this E naught e to the I kz minus omega t, and that's for the real part, but the imaginary part gives us something that goes as e to the minus kiz. And this e to the minus kiz means that this thing, as you propagate in z, this thing is going to decay. So this decay is absorption, because that means that the electric field is diminishing as this thing propagates through the material. So we're going to call the real part, we're going to relate that to the index of refraction, and that's just going to be given by here, where n is the total number of all these electrons that are, affecting the signal. Omega j is each of these states. So as we had before with an atom, we had, the 1s to 2p, and then 2p to 3s. That would be, the omega j, like omega 1 squared would be the 1s to 2p transition, and then omega 2 squared would be the 2p to 3s transition, for example. So we're going to sum over all those possible transitions, and then we have f of j here. It gives us the oscillator strength, and basically it's just a fudge factor. In certain cases, you can actually calculate this from quantum mechanics, but most of the time you're actually just going to be measuring this thing and then fitting some function to this. Okay, so that's the real part, gives us our index of refraction, and we also have the imaginary part, and so we'll call that the absorption, because that's the part that diminishes the electric field, and so that means that we're absorbing this electric field. And so this absorption, again, is proportional to the number of electrons that we have that are oscillating up and down here, but it's also proportional to that gamma, this damping factor. So whatever is causing this oscillation to dampen, that's going to dictate how fast this light gets absorbed. Okay, so hopefully that has clarified some of the concepts of what's going on when an electromagnetic wave hits some material and it gets absorbed, or you have some index of refraction and it changes the wave velocity. Okay, so looking at absorption a little bit more, what you get is a line that looks like this, and this profile is really close to a Lorentzian profile, or Lorentzian line shape. And if you're pretty close to this line width here, it actually ends up looking quite like a Lorentzian. And if you remember before, the Fourier transform of a Lorentzian was something that is a decaying exponential. And so what that means is that this absorption profile that we were talking about before, from Fourier transforms, is telling us in time that this thing decays exponentially. But that's exactly what we saw here, is that we end up having something that decays exponentially as this thing propagates through this material, and that's dictated by this absorption. So this absorption will, tell us how fast this light is being absorbed at this frequency. So this is consistent because we understand this profile in time, we understand this profile in frequency, and they're related to one another, as you learned from the Fourier transforms. Okay, so to finish off this section, we'll be talking about spontaneous emission. So the Larmor formula is the equation that gives us how fast this energy is dissipated by an accelerating charge. So an accelerating charge is what gives off radiation, but of course radiation carries energy, and so the Larmor formula tells us the rate of this energy loss, or power. So this power is given as 1 over 4 pi epsilon naught, 2/3 the electric charge squared times the acceleration of this charge squared divided by the speed of light squared. And this is equal to the rate of change of the electric field of the energy. So now we put this into the electron oscillator equation, and we get that the rate of change of the energy is going to be minus 1 over 4 pi epsilon naught, 2/3 E squared omega naught squared over 3 mc squared times the energy of this field. And so it turns out that this is just going to be a rate equation where this term here is going to be giving us the rate of the energy decay. So what that means is that the rate that the energy is lost is 1 over 4 pi epsilon naught, 2/3 E squared omega naught squared, so that's the resonant frequency, over mc cubed. So this isn't totally true. This is, kind of a good rule of thumb, or it gives us a good estimate. So in the visible region, because omega naught squared would be somewhere in the visible, so this would be 10 to the 15 radians per second, this would be something like nanoseconds, which is a reasonable number. That's about how long you can have an atom in an excited state for. But in reality, this actually depends on a bunch of stuff. So if you have really strong transition strengths, or the states involved, or even if you have this as like in terms of molecules or atoms, it'll actually depend on the pressure, because as soon as two atoms collide with one another, they can actually decay that way. So it's actually a pressure sensitivity. So this is a great oversimplification, but it does give us kind of an estimation of where this rate of this state decay comes from. Okay, so this is from the Larmor formula. This is how fast an oscillating electric charge loses energy. But what we also have, what we discussed before, was when we have, say, an atom in two states. So it has some electron that's in an upper state, and then this decays down to the lower state. So the rate of change of this electron from the upper state down to the lower state is going to be dependent on what the population is of that upper state times some decay factor, and we'll call that A21. So how fast it decays from N2 down to N21, or N2 down to N1, will depend on what that population is, and then also this rate of change. So this is kind of like thinking about it in terms of a quantum mechanical way. But the thing is that what we just calculated before was the rate of the energy lost from the system. And so the thing is that, well, this is also going to be releasing a photon as we go from this upper state down to this lower state that's releasing a photon, so that's releasing energy. And so what we can do is we can actually relate this rate of energy loss here to these rates of these states changing. And so we get that the rate of these states changing, this A21, is going to be 1 over 4 pi epsilon naught, 2/3 e squared omega naught squared over 3 mc cubed. And so what that's telling us is that the rate that these states change is related to the rate that these photons are given off, or the rate that this energy is lost from the system. Okay, so that's the rate of spontaneous emission. And so that's what I want to try and do is, what I'm trying to do here is link up this classical model that we've come up with for this driven damped harmonic oscillator and recognize that that's going to be giving us the information on how fast things are absorbed or how fast things are emitted from these states as they go from an upper state down to a lower state, or from a lower state to an upper state. Okay, I'll be finishing off this week with talking about a couple kinds of broadening. If you actually look at the textbook, I think broadening is covered in about 20 pages or so. I don't really care to talk about broadening because it's not particularly interesting. But basically, there are several kinds of broadening. The textbook talks about 2 of them. One of them is collisional. So if you have a bunch of atoms and they're in excited states and these things hit another atom, they can spontaneously decay. So that will change how long these states live for. And then Doppler broadening is that you have atoms whizzing around at various velocities. Those different velocities will give you different frequencies, and so that's called Doppler broadening. They are interesting, but they're not particularly useful in the way that I want to cover this course. So if you'd like to learn more, feel free, but I won't be talking too much about these in this course. But basically, in summary, they affect the line width of these transitions. All right, and this has run a little long, so I apologize for that. But hopefully, if you had further questions about how absorption and dispersion work, maybe this will clarify some of those points.